Testing, testing, 1, 2, 3. Is the correct camera being used? I think it is, actually. Kind of red for some reason. Eh. Can I go green? I think that's as green as we get. And all, well, it's not quite Halloween yet, so we should save our Halloween madness for Halloween. All right. What's that clicking? Tick, tick, tick. What's going on? Testing, testing, 1, 2, 3, testing, testing. Well, that was weird. I don't know where that was coming from. Good. Okay. I'm a little orange, but I don't have time to play with the hue slider, so I'll just have to be orange. So, good morning, everyone. How are you all doing today? Well, I hope. Let's see here. Oh, yeah. Yeah. Felix is, like, right here. So I think I'm gonna put him out of the room. Although, he's being quiet at the moment, but if you stay quiet, you can come and you can watch what your dad's doing. But if you start making noise, I'm gonna put you out of the room, okay? Okay. Alright. So it goes. Now here's a question. Which audio input am I using? Condenser mic. Okay, good. All right. Oh, there we go. So, is it a boy or a girl? It is a girl. Her name is Cordelia Shirley Pollard Moore. Felix is spelt with the first of those two spellings. Yes. Everybody's happy and healthy. The delivery went extremely well. It was a model of perfect delivery, to be honest. It was, you couldn't have asked for it to go better. It was very quick. My wife didn't require any kind of medical interventions or even drugs. Basically, she delivered the kid on nothing but 2 worn-off Tylenol, and that's how that went. It was extremely good. So yeah, yeah. Right now, she's, you know, asleep with her mum. We're having some trouble getting her to sleep in her bassinet, but, you know, she's also, at this point, less than 48 hours old, so, you know, so it goes. Thank you, everybody. Thank you. Yeah, so, yeah, that's, so pursuant to that, we are going to have our lectures online for a little bit, a couple of weeks, I hope. although I'd like to reserve the option of putting a third week on there. Okay, mister, if you start talking again, I'm going to have to put you out of the room, okay? Yeah, okay. Out of the room. He's not going to leave us alone, so. There we go. Yeah, so lectures are going to be online for a bit. I hope that's not too much of an inconvenience for everyone. But yeah. So, I was looking at the video that was taken of Mark's lecture. I am going to get that up on the channel at some point, though, you know, yeah, basically for obvious reasons, I haven't really been answering my email or anything the last couple of days, so if you have an email pending, I am going to get to your email. I just haven't had time. This is like literally, this is literally the first time I've been able to sit down at my computer since Cordelia was born, so at any rate, my impression was that Mark got through the linear square root material with you. Did he do Pythagorean triples? I saw that the video was only a half hour, which is in theory only half the lecture time. So I don't know if the video cut out short or something like that. Did you guys do Pythagorean triples? By the way, in the poll, the 22% of you who selected second baby are correct. She is our second baby. No, didn't do Pythagorean triples. Okay. Well, let's see if we can bust through this material then, shall we? Wonderful. So, good. The lecture was shorter because we had a first year. Oh yes, how did that go? The person who was presenting about first year. She said she was only going to take 10 minutes. Seems like she took more like 20. Well, at any rate. Hopefully that contained some useful information for you guys. So, Pythagorean triples. We continue on with our imagination of ways in which things can be computed, which is kind of the whole point. So, previously, you guys talked about the some ways that we can find approximate square roots, which is extremely useful because, you know, the alternative to being able to calculate a square root is to have to look it all up in a table, which, of course, you know, looking things up in tables can be quite efficient, as it turns out, but they do take up quite a bit of memory. So this, in this case, we're kind of focusing on more algorithmic techniques for computing things rather than just looking everything up. But anyway, so let's talk about the Pythagorean triple problem. So first definition, a Pythagorean triple is any triangle such that it forms a right angle triangle, right? However, we're interested primarily in integers here, or exclusively. So there are sort of a small number of fixed combinations of three numbers, which, when taken to be the sides of a triangle, form a right angle triangle. These are known as Pythagorean triples. So basically, a, b, and c must be integers and must conform to a squared plus b squared equaling c squared. So we're going to go through a few different ways we can calculate these Pythagorean triples. We'll be concerned primarily with finding those triples that exist underneath a certain threshold, right? So this is what you might call your brute force solution to the problem. Let me just let's just go in here. Not folder, geez. Oh, no. There we go. Code. I think the baby monitor is still on here. Give me a second. Yeah. I don't mean to brag anything, but newborn babies, like really newborn babies, like babies who are literally just born, are usually pretty ugly because they're all like wrinkly and squashed. But she's pretty cute even for a fresh newborn, I have to say. And you know, it is what it is. I might be flattering myself slightly because my genetic material or whatever. Also my wife. But yeah, anyway. So, Pythagorean triples. The algorithm in general, we define our... This is a live coding segment, so please feel free to code along with Prof. So, for... I'm sorry. We wanted to find all Pythagorean triangles with side lengths less than n. So, for a in range from 1 to n plus 1, for b in range 1 to n plus 1, for c in range 1 to n plus 1. If a squared plus b squared equals c squared, then print a, b, c. There we go. And let's just call triple on everything under 100. Yeah? Good. So, if we run this bad boy, there we go. You can see that actually took some time, but we get all of the Pythagorean triples for side lengths under 100. A lot of them are like various, this single triangle rephrased in various ways, but, it is what it is. So, the approach that this algorithm uses is to sort of iterate every possible triangle and then select those triangles which conform to the correct property. This is, this works, but the problem is that it's terribly, terribly inefficient. Basically, and I'm just gonna talk through these examples here. So, our innermost loop here is computed n to the power of 3 times, right? However big n is, n cubed is how many times this guy executes, which means that while it's, hypothetically possible to calculate, say, 1,000 of these, you can see that it's actually, you see how slowly it's doing that? how long it's taking to calculate these, right? That's because it's having, like, it's going through 1,000 cubed possible combinations right now, right? And 1,000 cubed, as we know, is 1 billion, which is going to take some time. So, we would like to come up with a way of improving this algorithm so that it doesn't take this long to do its thing. I'm just going to take this and run it over here in the background. There we go. Ha! So, essentially, a lot of the way that we talk about the optimization of algorithms is we take a look at the structure of the algorithm and decide, are we using too many nested loops? Can we compute what we need to compute using fewer nested loops, right? So in this particular case, we might make the observation that we don't actually need to calculate through, we don't need to iterate through every possible value of C. We can calculate the correct value of C, right? Now, if C comes out as an integer, if we compute the square root of a squared plus b squared, or approximate integer anyway, then we know that we are looking at a Pythagorean triple. Otherwise, if it has some kind of fractional component after we perform that calculation, then we know that it's not. So let's modify our algorithm to take this into account, shall we? Let's say, you can see that thing's still going, right? 222. So, let's take this guy out entirely. Let's say C is equal to this phrase right here to the power of 0.5. I know in the slides they use the binary square root algorithm that we developed, but, you know, I'm not. So if, let's say, C mod 1 is greater than some small amount, then we print it. Right? So this guy, I'm just going to terminate him because he's taken long enough. So let's calculate 222 instead. Oh, syntax errors. Jeez. Oh, okay. So we've got a problem. Not actually doing it. Okay. Let me just see what's going on here. I think I just inverted a less than there. Okay, I think I just inverted the less than. I think that'll be fine now. Smaller than the epsilon. Yes, thank you. Yeah, there we go. And if you really want to convert this back to an int from a float, that might make it look a little more clean. There we go. So you'll notice, whereas the other algorithm took longer than I took to explain this one to execute, we can execute this one in topic 6.py, you know, half a second, which is quite good, right? Wonderful. So, like, these types of algorithmic considerations are the difference between being able to calculate something in a reasonable amount of time and not being able to calculate it at all. In general, we aren't marking you for efficiency. We're just marking you for can you get the correct solution, but you know, if you have to wait around for your algorithm to finish, it can get quite boring. So there you go. Um, so that's one improvement we can make. We've improved this inner loop so that it now only takes n squared, right? Because the power of n is the degree of nestedness of the loop going on here, right? So, okay, but we might be able to improve this even further. So one thing that you may observe about these numbers that are being produced is that you'll get some things that look like duplicates. So, for example, let me see if I can find one. Oh, I've got so much scrolling going on now. I mean, the most quintessential example of this, of course, is 3, 4, 5, 4, 3, 5. It's not quite in the problem definition, but you might be able to say that these two entries which are produced do not represent unique solutions to the problem. They are, you know, if you were using fancy math language, you might say that these are isomorphic solutions. That is to say, having the same shape. So we can reformulate the algorithm in such a way to exclude these, while at the same time making it more efficient. And we can do that by changing a single character. Rather than ranging in this line from 1 to n plus 1, what if we ranged from a? You can see that our runtime has been cut in half. So, and this eliminates this double problem. So rather than starting from 1 each time, if we assume that b must be equal to or greater than a, then we're still exhaustively searching all possible combinations, but we're not including those unnecessary ones, and we managed to double our runtime, or sorry, half our runtime. Make sense? Any questions? Is it okay if our C is much higher than 1,000? Ah, C. Okay. So that's one thing that we do lose through these approximations. So previously, we were interested in all side lengths, all triangles with side lengths less than 1,000, because we're now calculating the side length, the third side length, rather than just ranging over from it to whatever we stop at. We are getting quite a few values that are over 1,000. If you want to exclude those, it's relatively simple. You just add an OR statement here, or, sorry, an AND statement. C must be less than n. So if C is approximately an integer and if it's less than n, then we print it. So if we print that, there you go. You'll notice, however, that our runtime has popped up just a little bit. This is because we are performing more math inside of the test, right? This expression now takes a little bit longer to calculate, and that we do it often enough that we actually see that come out in our runtime. So that's an excellent question. And you can see that now we've got like this perfect 3-digit, 3-column math thing going on. Right? Cool. All right. Thank you very much. C will kind of be constrained by the other ones. But yeah. So, good. Moving right along. Good. So, if we know how many steps a program takes depending on the input, we can use this to predict the execution time. This can be done without knowing details of the processor and compilation to machine language. And, you know, I think I've hit this point a few times already, but not just the details of the compiler and the processor, but details of the operating system, details of how many operating system processes are running, details of what the weather is like outside can affect computation, like levels of atmospheric humidity, you know, because if the air is more humid, then you have a faster decay rate of memory, which means it has to be, you know, the sub-processes which address memory decay have to be run more frequently. You know, there's just a lot of things that affect the runtime of an algorithm. So in general, we are concerned with the proportionality between the runtime of the algorithm and how many inputs you're processing. So you're going to learn all about this in second year. Incidentally, they get a lot worse than n cubed. 2 to the power of n is much, much, much worse than anything on this chart. And you even have a few algorithms, like the brute force traveling salesman problem, that have a worst case runtime of n factorial, which means you can only compute about 10 steps effectively. And maybe not even there. So, good. I'm just going to skip this stuff because we're kind of behind. So we'll skip right to careful with floating point. A few final words on being careful about floating point representations. So let's imagine we are trying to compute our old friend, the quadratic formula. Let's imagine that we are running the quadratic equation with these sets of parameters, right? So the b is -2 to the power of e, or -2 times 10 to the power of e, -2 times 10 to the power of 8, shall we say. We get as the roots of that equation 2 times 10 to the power of 8. That's 1,000 million, 200 million, and 0. But that is, if you were to take that and calculate that out, that actually doesn't work, right? If you were to substitute x for this number, that wouldn't produce a solution to this. Like, that would not equal 0. And the problem is this little +1, right? So, what's going on here? Well, the problem is in this little sub-expression up here, right? b squared minus 4ac. Because we've got a b squared going on here, -2 to the -2 times 10 to the power of 8 times itself is 4 times 10 to the power of 16, which, if you subtract 4 from that, you might remember how large floating point numbers can have a tendency to gobble up small floating point numbers or integers. So you can see that the loss of significant digits means that this is an incorrect answer. So that's what's going on here, right? Because of the intermediate steps of the calculation, have large values. These values are still susceptible to floating point representation problems. Incidentally, this would not happen with integers. So how can we avoid such errors? Well, we can use the decimal library for exact precision, which is slower, Or we can use an alternative formula that is more numerically stable and does not lead to large intermediate values. So you've probably never heard of this, but solutions to the quadratic equation are also related by Vieta's formula, given here. Given the solution with larger absolute value, the smaller can be computed using Vieta, avoiding the loss of significant digits. So you see we can calculate one from the other and avoid this problem. But of course, this is a solution to this problem that's very, very specific to the quadratic equation problem itself. This isn't something you can apply generally or universally. So and that's kind of true. These types of errors that crop up, if you're going to solve them by modifying the algorithm, then the algorithm itself, it is going to change dependent on the problem at hand. So it just requires intelligence and research. Are there any questions about topic 6 before we move on to topic 7? Why is this component not locked? It should be. Well, at any rate. Cool. I will assume there are no questions then. So, let's talk about testing and exceptions. So, testing then. It's important for you to realize that testing is it's a subfield within the software engineering community. It's not just a thing you do. There are testing specialists. If you want to, one of the things that you can do with your career is become a code analyst who tests software for a living, coming up with test cases, verifying the correctness of software programs. That can be that can be a job that you spend, you put in your 40 or 50 years till retirement, right? Testing is an extremely important thing to know how to do correctly. So we're going to talk about how, thus far we haven't really had a structured approach to software testing. We've provided you with test cases, but we're going to talk about some of the mechanisms by which those test cases are generated now, like some of the design philosophies that underlie them. So let's talk about testing. So let's consider the following program. Max product. It's kind of a facile problem, but essentially the max product function takes in a series of numbers expressed as a string. Expressed as a string, and outputs the product of the 12 adjacent digits which have the greatest product. So if we have, if we have some series of digits, the question we're trying to answer is, which series of digits, which series of 12 digits has the greatest product, right? So far as it goes, our algorithm to calculate this, for I in range from the length of s to the length of s minus 12, our product is equal to 1. We then test a subrange, right? Basically, we go through these one by one. At each step, we say, okay, I'm taking the next 12, calculate the product, compare that to the current maximum. If it's greater than the current maximum, replace the current maximum with the one we just calculated, and then move on to the next step. So in general, this would be a n squared algorithm because we've got two loops going on. But yeah, but the problem is this code contains a bug, and we're going to develop some methodologies to be able to find the bug in this algorithm. So, in general, in order to solve software problems, you need to know a couple of things. Number one, you need to know that the problem exists. Number two, you need to know where the problem exists. Number three, you need to know how that problem could be fixed. You can't possibly know how to fix a problem without having a good knowledge of where the problem is and what's causing it, unless you're fixing bugs by dumb luck, which is certainly possible. I remember a fair amount of my early programming career was spent fixing bugs by dumb luck. A thing that I would sort of habitually and ritually do whenever I had a bug was to re-implement a section of code using different code constructs in the vague hope that one of these variants would do what I wanted it to. I have since developed greater and more powerful methodologies in my own person. So how could we have detected this bug? Number one, make some test cases with known correct answers to see if this program produces the right answer. This is an approach that requires what we call an oracle. That is, someone has to know the right answer, right? The right answer, you might be able to derive that from your own brain. I know what this code should do in this situation, and it's not doing it. It could be derived from specification documents. It could be derived from clients. It could be derived from other pieces of software which are supposed to do the same thing even. For example, if you're trying to optimize code that is already correct, the code which is already correct can be used to test the code which you're optimizing. If it's known to produce the correct solutions, then you can compare the results of the old slow code with the new fast code to see that the fast code is still correct with respect to producing the correct values. So, you can also have another person independently implement the function and see if you get the same answer. That is something you will do in courses other than this course, or later on in your career, because we have quite enough software sharing in this course already. Thank you very much. We've started back down the path of convicting people of academic dishonesty, because there was quite a bit of it on the assignment 3 submissions, and you know who you are because you've gotten a letter. Do not copy your code from the internet. Do not copy your code from your friends. Don't do it. Don't do it. If I have to say it again, things are going to have to, I did warn you guys. I warned you guys at the beginning of the course that I actually do look for it and convict it. So, You have nobody to blame but yourselves. Another methodology for detecting bugs is to have some other third person, third party, read your code and see if they can just see bugs by inspection. Normally, the person that you get to read your code would be a senior developer or, ostensibly someone who knows what they're talking about. So, the goal of testing is to determine whether a program works as intended or not. The goal of debugging is trying to fix a program that you already know has a bug. So, the whole process of fixing software is divided into testing and debugging. Those are different activities with different goals and different things you do in order to achieve them. This is, in general, your cyclical model of software development, which is the one that most people use by default. So the sixth bubble, which is not listed here in the diagram, is figure out what the program does, right? Figure out what is expected. That might be from a client or from a problem description. You should have a good understanding of what the code you're trying to write does before you start to write it. After that, you write your program code. You see that it compiles, right? If it doesn't compile, you go back to here, fix it, and then try to compile it again. You keep fixing until you get past the compiler. Then we test it to determine if it works as intended. If it does not, we identify bugs, we fix those bugs in the source code, and then we retest. You should never, ever, ever assume that a bug has been taken care of without verifying that using testing. This is why you keep the test cases around. You absolutely must continue to test your program as you're fixing the bugs. Otherwise, how do you know if the bugs are fixed? So, in general, testing methodologies are divided into two broad categories: white box testing and black box testing. Personally, I kind of think of this as a bit of a misnomer. The thought that we're trying to convey by white box and black box has more to do with transparency than color, right? So in white, or perhaps level of light, in white box testing, you have access to the program's source code, and you can use the program source code to attempt to guide your testing. Right? So testing procedures which rely on being able to view the code, that's white box testing. Black box testing does not rely on knowing the program's source code. It relies only on the ability to put input in and see what the output that results is. Right? So all of the testing that all of the test cases that we give you on your assignments, these are all black box tests. They assume no structure. They assume that your program, your function, has not been structured in any way whatsoever, unless that has been specified in the question. A good example of that is, of course, the recursive questions that require you to actually use recursion. In those cases, we are assuming that you will comply with the question and use recursion. But other than that, you're basically free to come up with any way that you wish to solve the problem, so long as you're not copying source code from the internet, Chegg, Stack Overflow, any of those sources. And, yeah, black box techniques. Black box techniques are, in general, very, very powerful for early testing. However, if you want, like, white box testing can provide a higher degree of reliability, shall we say, than black box testing. Both, in fact, all forms of testing require a clear specification of the program's expected behavior. The program needs to behave in a particular manner that needs to be codified and written down somewhere, and you need to use that information to guide your testing. So, let's talk about black box techniques first. Black box techniques do not rely on knowing the program's source code. They only rely on the ability to put in an input in and see the corresponding output. This is kind of why, this is also the reason why we're so strict about not having input functions inside of your assignment submissions, and not imagining that printing things using print statements constitutes real output. From a black box testing perspective, putting the output in the wrong place is the same thing as not producing any output at all. Focuses on the development of test cases to see if the actual output matches the expected output for a given input. So, if test cases are all you have, you need to be able to produce them reliably and to produce them effectively. So, I know I've beaten this drum quite a lot, but our general software design principles, once again, are modularity and decomposition. We need to be able to break programs into parts that are reasonably self-contained, achieve a clear purpose, and can be reused. And, of course, abstraction. We should be able to use parts of a program without knowing how they've been implemented, right? So, again, pieces of software should click together like Lego. You shouldn't have to think too much or too hard about how the Lego is actually constructed. You should just be able to snap them together. So, black box techniques are natural when the program has been designed well. If we take our program and break it into small functions, right, those functions, basically the smaller the function, the more easily it can be tested and debugged, right? That's why we want to break the program into many small functions. The larger the program gets, the more difficult it is to find bugs in it, and the more sort of abstruse the output is from the input, right? So, modularity enables better black box testing. So we're going to go through several different types of testing now. Developing test cases for each function within a program to ensure the individual function works as expected is called unit testing. So the test cases that we have provided for your examples so far, for your assignments so far, these have been unit tests. Of course, a large program will be composed of many small functions put together in some manner to produce a larger function. When you test to see if the software modules and components have been assembled correctly, and when you test to see if the program as a whole behaves as you expected, this is called integration testing. So if we are talking about a video game, for example, the Marios, unit testing would be you set up sort of a field of play with every enemy in it, and you have Mario jump on every enemy, and you see that each enemy has the correct reaction to Mario jumping on it, right? If Mario jumps on a Goomba, he wins. If Mario jumps on a Spiny, he loses. And that's how you test that. You test each individual thing. Integration testing is more like You start up the game from scratch, you go through the menus, you select a level, you play through that level, you note anything that goes wrong as you're playing through that level, create a list of these problems, and then that will be a list of bugs to be fixed. That's more like integration testing. We also have a concept of regression testing. So, bugs are tricky entities. You may think that one is solved, but you may not have solved it permanently. We kind of recognize a distinction in software between true solutions to problems and what we call kludges. This kludge is actually like a software term. Some people call them kludges, but it's spelt kludge like fudge, so that's how I'm pronouncing it. But you can see kludges have their own Wikipedia article. So a kludge is a workaround or quick and dirty solution that is clumsy, inelegant, inefficient, difficult to extend, and hard to maintain. The term is used in such diverse fields as computer science, aerospace engineering, internet slang, evolutionary neuroscience, and government, particularly in government, shall we say. It is similar in meaning to the naval term jury-rig. So this is an famous example of a kludge. If you have a bridge that falls down, you just build the second bridge over top of it. This is a terrible solution, but it does render the bridge temporarily usable. When you produce a kludge, you don't actually fix the problem. What you do is you come up with some kind of trick that avoids the problem, which means the problem can pop up again later. Regression testing is what we use to expose these bugs once and for all. Okay, so that's it. If you have any questions, please ask them on Piazza. I've got another class to get to. But yeah, thank you very much, folks. I'll see you in the next one.